Hello and welcome. This is Mr. King. I'm going to be recording a quick video to talk about lenses and refraction and to kind of give you a little bit of spearhead on practice problems involving Snell's law and focal distance, etc., with thin lenses. So all of this can be found, materials for this can be found in the week 1 packet post I made on Google Classroom. We're going to be looking at chapter 14 slides as well as the mirrors and lenses PDF. The physics checkpoint 8 formulas are going to come in handy just as kind of a place to refer back to. I'm going to also be looking at Snell's law practice problems and lenses practice problems. So I'm going to be kind of jumping through the slides on the presentation here because most of it I don't find particularly useful, but you're welcome to go back and take a look at it. Of course, you should already know by now that when light bends as it moves between two different media, say from air into glass or from air into water or other such, that bending is called refraction. Now, whenever light is refracted, its direction is changed, having to do with the speed of light in different media. Now, when we quote the speed of light as 3 times 10 to the 8th, we're assuming that it's moving through a vacuum or a near vacuum. However, that changes depending on the medium the light's passing through. And so we start looking at something called the index of refraction. Index of refraction we're going to refer to with the variable n. The way they find the index of refraction is they take the speed of light in a vacuum divided by the speed of light in that particular medium. Now, since it's going to move the fastest through a vacuum, this speed here is always going to be lower, so n is always going to be greater than the number 1. Or for a vacuum or for a near vacuum, n is going to be very equal to 1. This right here is just a table of some different values of n. For the most part, anytime we have a practice problem, these will be given. But if you needed to find the index of refraction for a certain substance, you would be able to either refer back to this chart or just Google it. Now, we do need to talk a couple of terms here real quick. We need to talk about something called the normal. So let me swap over to my camera and I'll explain what that looks like. Let's say that you've got an interface between two substances, okay? We might say that this substance right here is air and this substance right here is water. Now, whenever light comes in and hits that substance, hits the interface between those two substances, a couple of different things can happen. One, the light may be reflected. Now, we're going to draw a line perpendicular to the surface of our medium. You already know in reflection that the angle of incidence, meaning the angle that the light ray strikes that reflecting surface, is going to be the same as the angle at which it's reflected. So we know that this angle right here is congruent or equal to this angle right here. However, not all light is going to be reflected if you've got a substance that allows light to pass through it. Instead, what's going to happen is that it is going to be bent. And so when we talk about this right here, which is a imaginary perpendicular line to the surface of our medium, we refer to this as the normal. If you recall earlier this year in physics, when we talked about normal force, that was force that was acting upward perpendicular to the surface that an object was resting on. Well, a normal here, in a similar way, it's perpendicular to the surface that that light ray is passing into. We refer to this first light ray right here as the incident light ray, meaning this is what it's starting with. And then this right here is going to be the refracted light ray. And we're curious about two angles here. One angle is this right here, okay? This right here is referred to as theta little I. Okay, let me see if I can zoom in any more there. Theta little I means angle of incidence, and it's measured between the normal and that incoming light ray. The other angle we're interested in is this one down here. This is referred to as theta sub r, or the angle of refraction. Okay, so everybody is clear on that? Let me swap back to the slide we were just looking at. This is very, very important. When light passes into a medium that has a larger index of refraction, then what happens is that the light ray bends toward the normal. In other words, the angle of refraction is going to be smaller than the angle of incidence. If, however, it's just the opposite, if light passes from a medium that has larger refraction to one that has smaller refraction, like light passing from water into the air, then the light ray is going to bend away from the normal. So in other words, this refracted angle would be larger than the incident angle. And we'll look at some different examples of both of those. So there's nothing to fear or fret yet. Here's a couple different examples. For example, this right here, when air has a lower index of refraction, then the theta r is going to be smaller than the theta I. If light is passing from glass back to air, then the theta r is going to be larger than the theta I. Now notice that some of that light gets reflected, because not 100% of the light striking the interface between two different media is going to pass through it. You know this if you've ever looked at a piece of glass. You know glass reflects things, as does the surface of, say, a body of water. So you don't have 100% refraction. Sometimes you do have 100% reflection, and we'll look at that more at a future talk. Now, it's very important that we talk about something called Snell's law. Snell's law is going to be a very easy equation that you're going to use to determine angle of incidence versus angle of refraction whenever light's moving between two different media. And it's super duper simple. The formula is index of refraction for your starting material times angle of incidence, or sine of angle of incidence, equals index of refraction of your new material times sine of the angle of refraction. So if you know, I believe if you know any three of these, then it is not difficult to find the fourth one, just by using a little bit of algebra, plugging in what you have and finding what you don't. We'll look at a few Snell's law practice problems here in just a minute. This is a fun slide because this is all about perspective. From the cat's perspective, even though the fish is actually here, the fish appears to be right here. Maybe I'm getting that different. Okay, from the fish's perspective. No. Okay, from the cat's perspective, it looks like the fish is here when the fish is actually here. From the fish's perspective, it looks like the cat is actually here when the cat, in fact, is right here. So refraction can actually play different tricks on your eyes depending on where you happen to be. We're going to look at a few sample problems. I'm not going to bother looking at the ones that are in the slides here. Instead, what I'm going to do is I'm going to look at some practice problems from this other paper that you got. Okay. I'm going to look at a couple of these because they do get slightly more complicated. I had some students buzz in and ask me about this a couple of days ago. They were a little bit ahead of the game. But even with the tricky ones, it's really not that tricky. So let's see. I'm going to just, let's go ahead and just do number one. Okay, a lot of extra information here. An old Greek superstition was that amethyst would protect those who wore it from drunkenness. We don't care. Deep colored amethyst is highly prized. Don't care. Here's the important part. Suppose a ray of light traveling in air strikes the surface of an amethyst crystal. If the ray makes an angle of 35 with the normal, what's the angle of incidence? So what we're going to do is we're going to transfer that over to our own paper, and we're going to jot down what information they give us. Okay, so we start off that it's traveling in air. So what that tells me is that if we're going to say that Ni times sine theta sub I is equal to Nr times sine theta sub R. Since it's traveling in air, we know the index of refraction in air. For our purposes, we can just call it 1 because air is close enough to a vacuum here. Looking back at our problem, it says that it strikes an amethyst crystal. Amethyst has an index of refraction, or N, of 1.553. So let's say that N sub R equals 1.553. It says if the ray in the amethyst makes an angle of 35 with the normal, what is the angle of incidence? So we're looking for N sub I. I'm sorry, no, we're looking for theta sub I. Okay, so theta sub I is our unknown. We know that the angle of reflection was 35 degrees with the normal. Okay. So in other words, this is our 35. This right here is what we're trying to find. And we know the indices of refraction. So if I rewrite this equation to solve for theta sub I, then I will divide N sub I from both sides. Sine of theta equals N sub R times the sine of theta sub R over N sub I, which is just 1. Now to get rid of that sign, remember we're going to have to do an inverted sine times both sides. So it's going to be theta sub I is going to equal all of this mess right here, N sub R sine theta sub R over, that looks like an H, N sub I to the sine of the negative 1. Okay? So, plugging in my numbers right here, that means that I'm going to do sine of the negative 1 of, I'm not sure I wrote that in the right place. That might actually need to go on the outside of that. I'm not too worried about how to write it. Let's plug in numbers here. My angle of refraction in my amethyst is 1.553 times, I need to do the sine of 35. All of that is going to be divided by 1. And I'm going to take, I think it is actually over here, sine to the negative 1 of all of that. So coming along, waking up my calculator. So I'm going to start off I'm going to save this for the very last step, and I'm just going to get all of this mess right here. So I'm going to go 1.553 times sine of 35, and then divided by 1. I don't have to divide by 1. It's just going to give me the same answer. So I've got 0.89. Now I'm going to do sine to the negative 1 of this. So I'm going to hit Shift, sine, answer. And it tells me that my angle of incidence was 62.97. Okay, so I'm going to say that theta sub I equals 62.97 degrees. Now let's see if that makes sense. We're moving from something that has a lower index refraction into something that has a higher index refraction, which means that the light ray should get bent toward the normal, meaning that this should be smaller than this. And if this is about 63 and if this is about 35, then it certainly fits with what we'd expect to find. Okay. Let's look at another slightly trickier question. Sometimes it can move between several different media. Let's see here. Do we want to look at... let's not look at number 8. Number 8 is just asking you to work 2 problems. Oh, I like number 9. Let's look at number 9. Number 9, amber is a fossil resin of trees that lived tens of millions of years ago. Sometimes insects were trapped by the resin and fossilized inside. So suppose a ray of light traveling in air strikes a 2 millimeter thick clear amber pendant, amber having an index of refraction of 1.54 at an angle of 17 degrees with the normal. Find the angles of refraction at each surface. I love this. So I'm going to record a couple things on my paper, and then I'm going to swap camera. I'm going to record that Ni, or N of air, is equal to 1. I'm going to record that N of amber, see if I can spell, is equal to 1.54. And I'm going to record that my original angle of incidence is 17 degrees. Okay? Now, this is a little bit different because what's happening is that we're going to say that here is our amethyst. Okay? Let me kind of shade it in a little bit. We have our air out here. We have our amethyst right here. So let's go ahead and get a line of normality right here. So light is going to come in and strike this at an angle of 17 degrees. Okay? Now, because this has a higher index of refraction, we're going to assume that it is going to get bent in toward the normal. So our theta sub r is going to be less than 17. Now, something's going to happen, though, because it's going to pass through this piece of amber. When it passes through this piece of amber, then it's going to exit the amber back into the air. And when it passes from the amber back into the air, then it's going to be refracted again. So this angle here is going to be our new index of refraction, or I'm sorry, our new angle of incidence, and then we're going to have another angle of refraction right here. So we're going to have to actually take this as 2 separate problems. We're going to start with this first one. I'm going to call this first change right here change number 1. I'm going to call the second refraction right here refraction number 2. So we're going to start with number 1. And we're going to say, again, using Snell's law, that n sub I times sine theta sub I equals n sub r times sine theta sub r. So we're looking for starters at, we're looking for theta sub r. So rewriting all of this mess, we are going to get that we need to do sine to the negative 1 of n sub I times sine of theta sub I over n sub r. And that's going to give us theta sub r. So plugging all this in, we're going to need to do sine to the negative of, okay, our first index of refraction is 1, so 1 times the sine of 17, because that was our angle of incidence, divided by 1.54. So let's calculator that. Okay, again, I'm going to do what's inside here, and then I'm going to do invert sine to that after I do so. So I'm going to start with sine of 17 divided by 1.54. Okay, that gives me this number right here, and so when I negative sign that, so I'm going to go sine to the negative of my answer, I get that my angle of refraction is 10.94. So for this first interface right here, this new angle is going to be 10.94. Okay, so 10.94 degrees. Now I want to point out something kind of funny. If you notice right here, what I've got is I've got two parallel lines, and there is a line that is coming through and making an angle with both. Now, if you recall from your geometry lessons, that means that this angle here, which is our angle of refraction, is congruent with this angle right here, which is our new angle of incidence. Okay, if you don't believe me, go ask your geometry teacher. So now we're going to do part 2, and it's going to be almost exactly the opposite. What's going to happen is that the light is moving from the from the amber back out into the air. So for this right here, our index of refraction of what we're starting with is 1.54. Our new index that it's going to be refracted into is 1. And our angle of incidence is going to be 10.94 degrees. And we're trying to find our new angle of refraction. Okay. At this point, some of you might be wondering in your brain if it can really be as easy as your brain thinks it's going to be. Let's just find out. Let's go ahead and take our Snell's law equation, n sub I times sine theta sub I equals n sub r times sine theta sub r. We're solving for theta sub r. So it's going to be pretty much exactly the same equation that we used a minute ago, except we are swapping around some of our values. And so I'm going to skip a few steps. I'm going to say that theta sub r is equal to invert sine of, this time I'm going to do 1.54 times sine of 10.94 divided by 1. So let's see what the calculator tells us about that. So 1.54 times sine of 10.94. Now I'd be dividing by 1, so I'm going to leave that step off. That gives me 0.2922, so when I do negative sine of that, wait for it, what do you think it's going to be? 16.99. Now, 16.99 is awfully close. Anybody? Awfully close to 17. So in other words, check this out. Looking at this entire thing, if it's coming in at an angle of 17 degrees into a medium that has two parallel lines making up its two surfaces, then it will exit at the same exact angle. The only difference is that in the meantime, it's going to be bent a little bit this way, but then it's going to pop right back out at the same angle that it entered. Okay, that's a super important thing to remember. I'm going to pop back into our, actually, I'm going to skip out of the presentation and talk a little bit about the math of lenses. The good news about the math of lenses you're going to find is that it is an awful lot like the math of curved mirrors. You are still talking about some of the same equations with your involving the distance of your image and the distance of your object, including focal point. The difference here is that if you have a lens and light is passing through it, you actually have two focal points. You have a focal point on each side of the lens. Okay, you can use ray tracing to predict where and how an image is going to form, just like you could with your mirrors. In this case, what you're going to do is you're going to use both of your focal points, one on either side of your lens. And so you take one ray at the top of your object, take it parallel, and then once it hits the plane of the mirror, it bends toward the focal point on the other side. You've got one that is going to go through the focal point on your own side until it strikes the mirror, and then it is going to pass through the other side. Now, we've got something new right here. The M ray is actually going to pass through the center line at the center plane of that lens without being refracted. And so all of these are going to form right here, which means that the image that you're going to get from this particular one here is going to be inverted. Now, because these light rays are converging, you're going to get a real image. It's not going to be a virtual image. It's actually going to project it upside down at this position right here. Just like there were two kinds of lenses, two kinds of curved mirrors we talked about, convex and concave. There's also two types of lenses. You have what's called a converging lens, which refracts light rays toward a focal point. You also have a diverging lens, which as light rays pass in there, they are bent outward. This is a lot like your convex mirror. And so when you're visualizing this, you use the focal point that's on the same side, and as they're bent outward, you would sort of reverse trace that ray back to that focal point. If you're not sure what I'm talking about, I dropped about a 5 or 10 minute video illustrating light that's being bent by lenses and by mirrors. You need to go take a watch and see what you see there. A couple different things can happen. You can have, right here we've got a converging lens, and if the object is past the focal point, then the image that's going to form is going to be inverted and real. If the object is between the focal point and the lens itself, though, then the image that forms is actually going to be on the same side as the object. It's going to be larger, and it's going to be virtual. It's not going to be on the opposite side of the lens. And it's not coming from light rays that are crossing back to a central point again. So you can see right here, this is bent that way. This one is not bent at all as it passes through there. So these two don't end up converging, but the back halves of them both do. A good example of this would be, well, let me just see if I can show you what I'm talking about here using some real world stuff. Okay, if I have my object, I'm just going to call my object. I'm going to start. Let me see if I've got a lens here. I think I might be able to use this. Okay, so I'm going to put this lens on top of this. Now this lens, if you look at it, is a converging lens. If I place it on top of my object and I slowly raise it up, then the image I'm seeing actually appears to be farther away than it is, and it seems bigger. Now, if I continue moving that object past my focal point, it seems to get all scattered and weird. But then if I keep bringing it up, oh, what happened? You see it? You can just barely make it out right there, but the word object that I wrote is backwards. It's reversed. If I turn my lens like this and bring it up, it gets bigger and bigger and bigger. And now it's upside down. What I'm seeing right now is a real image that's being projected through that lens toward me further up here. If it's between the focal length and the thing, though, then it looks like it's the same thing. It just looks bigger than it was. I'm seeing virtual image there, real image here. Okay, I know that probably raises a lot more questions than it does actual answers. Bear with me for a minute, though. Now this ought to look really familiar to you. The thin lens equation says that 1 over the distance of the object plus 1 over the distance of the image equals 1 over that focal length. And there's some rules for that in this handout that you got. Let's take a quick look at the physics checkpoint formulas, okay? Because I have a feeling that we kind of sissied out on something the other day, and we just said, oh, this is evil, we couldn't possibly work this. We have on this formula sheet, we have Snell's law. We have, of course, the general wave equation. The velocity of a wave equals its frequency times its wavelength. Now, these are true for lenses and curved mirrors. 1 over distance of object plus 1 over distance of image equals 1 over focal length. Magnification factor is equal to the height of the image divided by the height of the object. And that's equal to the negative distance of the image over the distance of the object. Now, keep in mind, your height, if the height of your image is negative, that means that it's going to be upside down, okay? Or in other words, if your M is negative, then your image is an inverted image, but it's also a real image. Now, here is something that we didn't really touch on the other day, and I'm kind of smacking myself that we didn't. Look at this little formula written down here. This says that for a curved mirror, if you're trying to find the distance of an object and you know the height of that object and the height of the image that it projects and the focal length of either the mirror or the lens, then you can use this equation right here to find the distance of the object. Several of those problems that I showed you the other day that I said, oh, these are evil, if you use this, you can actually work those. So we gave up way, way too quickly. I'm going to set this to the side, and we're going to take a look at some of these lens practice problems, knowing what we know. Now, I'll go through later and see if there are any of these that are deeply objectively evil, but I have a feeling that none of these are going to be as hard as we maybe think they are. So let's look at number 1. An object is placed 13 centimeters in front of a converging lens. Okay. The image forms 19 centimeters behind the lens and is 3 centimeters tall. So determine the focal length of the lens and the height of the object. Let me just jot a couple things down on my paper. Okay. Object is placed 13 centimeters in front of a converging lens, so the distance of my object is going to be 13 cm. Distance of my image is going to be 19 cm. And my image is going to be 3 centimeters tall. Okay? It says it's a converging lens, so let me swap over to my paper here. So here's our object, here's our converging lens. We note that the distance of the object is 13 centimeters. Okay? We know the height of the image that we're going to get is 3 centimeters. Okay? We're still, at this point, I'm not sure if that means the image is going to be forming on this side or on this side. I'm going to presume, since they didn't give us a negative height, oh, they didn't give us a negative height. So this is going to be a virtual image. So the image is going to be somewhere on this side, along with the object. Okay? I'm going to presume that the image is going to appear behind the object, but let's see what our formulas tell us. The formulas we're going to use, remember, 1 over dO plus 1 over di equals 1 over f. We know that for magnification, magnification equals the height of our image divided by the height of our object, which is also equal to the negative distance of our image over the distance of our object. So let's check back again and see what did they want us to find. They want us to find focal length, and they want us to find height of the object. So we're trying to find f, and we're trying to find O. So given what we've got right here, I think what we can do is we might be able to find the height of the object by finding our magnification and finding what's the ratio of the distance of our object and the distance of our image. So let's start with that. Let's start by saying that m equals negative di over do. Actually, I'm going to save myself a step. Instead of going from this to this, I'm going to just use these two in an equality. So I'm going to say that height of image over height of object equals negative distance of image over distance of object. I'm trying to find height of object. So if I rewrite this equation, multiply both sides by height of object, I'll get rid of it over here, and then I can, well, let's invert this. This will make it that much easier. So let's say that ho over hi equals negative do over di. I'm trying to find ho, then I can multiply both sides by hi. Get rid of that. So let's say that this is going to be equal to negative 13 times 3 divided by 19. Okay? 13 times 3 divided by 19 equals, and I get, for my height of my object, I get negative 2.05. Okay, so I was wrong about this part up top here when I said that the image was going to be on the same side, since the height of the object has an opposite sign of the height of my image. What that tells me is that my image is actually over here. And since one of them is set like that and the other one is upside down, I know that my image is a real image. Okay? So my height of my object is negative 2.05 centimeters. I also need to find my focal length. Now, since I've got do and di, it's going to be easy enough to swap those in there. Apologize for the mess. So I'm going to start with 1 over do plus 1 over di equals 1 over f. That means that 1 over 13 plus 1 over 19 equals 1 over f. When I get into my calculator and I actually solve for 1 over f, I'm going to do 1 divided by 13 plus 1 divided by 19. I get this interesting decimal answer. Now that's 1 over f. So to invert it, I'm going to do 1 divided by my answer. So that tells me that my focal length is going to equal 7.72 centimeters. And I have solved for that. This video has run a little bit long, and so I'm going to go ahead and wrap it up. If anyone has any other questions, feel free to catch me during one of my regular conference times, and I will talk to you soon.